Hello world, Christian Truther here, and I've got another video for you today, part 9 of my series on the shape of the world. Is it round or is it flat? Can we determine what the shape is? The fact is, there is a true shape of the world, and we need to understand what that is and hold on to that regardless of whatever we thought it was. And so I hope you guys are approaching this with honesty, with actual curiosity, actually hoping to maybe learn something, because I will be telling you guys the truth. I'm not going to intentionally deceive anyone. If I make a mistake, that may be, and you guys can point it out in the comments, but I'm not going to deliberately mislead anyone. Also, I'm not going to insult anyone. So these are my ground rules, and the bottom two, by the way, apply to you guys in the comment section. Let's treat each other with the civility and respect that we all deserve. Now, I always recommend looking into my first video because I go over why I'm doing this and how I'm going to be doing this. All my videos tackle different subjects. This is my 9th, so there's plenty to look into. In this one, we're going to be looking at mathematics, but before we really get into it and start arguing, each side and seeing which one wins, I just wanted to also remind you guys that I don't do this with scripts or cuts or green screens or anything like that. I've seen a lot of that elsewhere. People trying to improve their arguments, I think. I'm not going to do that. I'm just going to tell you guys what I've reasoned out. And every subject, although you may have heard this subject before, I always try and bring something new to the table. Something that I had not heard before. So, try and see if you can catch that, and maybe it will cause some thinking to go on, and maybe you guys will realize that, something I've said makes more sense than something you believe. Or maybe it'll just bolster your belief. We'll see. But let's approach this with honesty, and let's treat each other with respect. Those are the most important things. So, as I said, this is going to be math by the numbers, and we're going to be looking at see what the math says. But math, what is math? Well, math is supposed to actually provide clarity. I understand if you don't understand the mathematical principle behind something, math can get confusing really fast. But if you do understand the principle, it's supposed to provide clarity on a situation. So, how many bananas you have, that's going to be quantity. It also is supposed to measure size and distance and velocity, some measurements. Also, relationships. How do things relate to each other? So, for instance, H2O, when it's liquid, it's got a certain known density. We call it water, and then density range. And then when it freezes, it starts turning into a crystal, and it expands, and then the density decreases, and that's why ice floats in water. And the relationship between temperature and density is well known. So, let's get into my first topic, which is going to be on drop, altitude, and bulge. And I bring this up because I've seen some of these terms used kind of interchangeably, and we need to understand clearly what they are. So drop is the measure of downward curvature on a circular or globular surface. It's going to be a vertical measurement on a circular surface. If it's being applied to a globe earth model, which it doesn't have to be, it could be, circle on this ball, but if it's going to be applied to a globe earth model, then the expected drop would be 8 inches squared per mile. That is the accepted average drop over distance. Altitude is the measure of height above the level of the seas. So that's going to be a measurement of height. If you use uphill or downhill, you should be referring to altitude only, not drop. Altitude is the measure above the seas. And then bulge is the measure of a rounded swelling. So if you take 2 points on that ball, that swelled surface, that's going to be the measure of the bulge. So let's take a look at how that plays out in a globe earth model. We have drop, measured in red. We always put the observer at the top and what they're trying to observe down around the side of the circular surface. And the vertical distance here is the drop measurement. Like I said, on the globe earth model, it's supposed to be 8 inches squared per mile. Then we have altitude. That'll be this over here. Anything that's above the level of the sea. And then bulge. That's, again, we have the observer, what they're attempting to observe. Bulge is going to be what's preventing them from seeing each other. That's not drop, that's bulge. And that is going to be the bulge. Okay? So, on the flat earth model, things are much simpler. We don't have to calculate drop because there's no drop. It's a flat plane, right? Altitude, well, we've got the measurement above the plane. Bulge could come into play in a flat earth model if you're measuring hills or a mountain range, something like that. But over the scope of the whole thing, bulge doesn't really play a factor either. So that is the different terms and how they're supposed to be used, and we can see plainly that drop can't be used in flat Earth model at all. Altitude definitely can be used in both, and bulge can only partially be used in small portions of a flat Earth model to describe maybe a swelling of a certain area of it, but not of the whole thing. So how does this apply to reality? Let's take a look at Toronto, across the water, Lake Ontario from Grimsby Beach. Please note the CN Tower is going to be the primary focus because it's obviously the tallest thing in this view and it's the most recognizable landmark. Now, what are some facts? The distance is going to be about 35 miles and the height of that CN Tower is about 15 feet. So that's a measurement of altitude. The expected drop over the distance of 35 miles using the 8 inches squared per mile is going to be about 817 feet. You can calculate that yourself. You can calculate the distance from Grimsby Beach all the way over to Toronto, just using Google Maps or whatever map software you want to use. That's going to be about the distance. So, that doesn't seem to match reality, does it? 817 feet is approximately half of that CN Tower, and this is a picture of it from the bottom to the top. I don't see that over here. So we have a strong argument for the flat Earth model because we do not see like half this tower getting cut off. Kind of looks like the whole thing is there. And is that all? Well, remember we were talking about some other variables. I just want to real quick plug in a couple of other things for you. So we still have 35 miles, 15 feet, and 817 feet of drop. But the CN Tower's base above sea level is 235 feet. So now the altitude is 2,040 feet approximately. Also, bulge is what actually denies the observer the ability to see something, not drop. Drop would help us calculate bulge, but it's not what's preventing the observer from seeing something. Bulge is, and so the expected, based on a 6-foot height of the observer, the expected hidden amount at that distance would be about 576 feet, of which 235 feet was ground. So the missing is 341 feet. That's what's missing. And now that starts to come into focus and that starts to look accurate. And here's why it's accurate, because there are docks in front of Toronto. You don't see them. There's an island in front of Toronto in between Grimsby Beach and Toronto. You don't see it. Also, there's something else really important you don't see. This nice object here, which is less than 340 feet, but about at the same altitude ground level as the tower, it's less than 340 feet. You don't see it in the frame. Now we understand that the round Earth model has won this round because they correctly predicted what we were not seeing in the shots. On a clear day, with a good view of everything, you're missing 500 and something feet of that tower from altitude. 570 something feet of altitude appears to be missing. 200 something feet was ground level, and then the rest is part of the tower is missing in the surrounding area. The round Earth predicted this exactly. So the round Earth wins this one. Also, let's take a look at a different subject, drop rate. Now, for people who believe that gravity doesn't exist and that density and buoyancy alone governs things, I've got a question for you. Here's a ball. It has mass in three-dimensional space, that's why the volume is cubed. We've got the density of this ball described. Suspension height is its distance to the ground. Where in this equation is motion? It doesn't exist. That's where Newton came in. Newton described 32 feet per second. And that provides the motion to the equation. Everyone agrees that density and buoyancy is involved in the dropping of this ball. Or should agree. It's absolutely involved. Its air resistance is going to be involved in density and buoyancy in particular. But there is a rate of acceleration of 32 feet per second before air resistance is factored in that this ball is going to adhere to, and everything on planet Earth is going to adhere to. And that's how things work. That's how tanks hit each other. That's how artillery from battleships strikes their targets. You needed this down here, what we call gravity. You needed that in the calculation because density and buoyancy alone did not provide anything for the rate of descent. Now I'm going to get into astrophysics for a second here. Christian Huygens, and yes, he has got 2 A's in his name, In 1653, he guessed that Venus was about the size of the Earth, and he used that to determine the distance to the Sun. He was pretty close, about 7% off, when the three formed a right triangle, and he was trying to be clever, and he figured, well, Venus is about the same size as Earth, and then I can base its distance based on that, and so now I have distance, and I've got two angles because it's a right triangle, and I point at the Sun, I point at Venus, I've got an angle there, and so now I've got the angles and I've got a leg. I can now determine the c² end of the triangle straight to the Sun, and I can figure out the distance. He was pretty close, which is pretty good with the tools he had at his time, but he guessed. That's why science doesn't credit him with the discovery of the distance to the Sun, because he guessed that Venus was about the size of the Earth. He could have been wrong. Turns out he was about right. But Cassini came along a little bit later, and he's credited with the actual distance to the Sun. He came up with a calculation that was even closer. It's about 5% of what we believe it to be today, using parallax or angular measurements, measuring in two different locations of the same thing at the exact same time, can create a 0 point. And they use that to determine the distance to the Sun and other celestial bodies, he and an assistant. So he is credited. Why am I even talking about this? Well, I'll get to that in a second. Isaac Newton in 1686, proposed universal gravitation in his Principia Mathematica, based on two objects of mass interacting with each other. The important thing about all this is that these guys were supplying necessary variables to an equation, and they didn't even realize it. See, Kepler's third law is stated thus, that time of orbit and the radius would always equal a number that he didn't understand, but it was the same for all the planets in the solar system. Kepler came up with this in 1608. He knew something was up because he could always take the time of their orbit and their distance by scale. He didn't know the exact distance, but he could scale it, and he said, the number always comes out the same. I don't know what this number is over here, and I don't know what the actual distance is here, but something is up here because by scale, these planets all have the same number that he called K. Well, he had pi squared, and he had elements to this equation here, but he couldn't rectify it completely. And along comes Cassini, and along comes Newton. And to a very high degree of accuracy, they provide numbers quite independently that allow the solving of this formula. See, Kepler described what was happening in 1609 with his law of planetary motion. Newton described how that motion occurred with his law of universal gravity. And then later on, Einstein came along and he described the mechanism, because Newton himself was like, it doesn't really make sense to me that these things would be attracting each other. That doesn't seem to make sense. And Einstein says, like, well, they're actually not attracting each other. They're warping space-time. And I'm not really going to get into that because that's also a mind-blowing thing. But the important thing is that Cassini and Newton were each supplying variables of an equation independently. They didn't realize that they were both working towards the same thing, to solve a big problem that someone else had found most of the information on, but were missing crucial variables. He needed the gravitational constant. He needed distance, and those numbers needed to be accurate and plugged into the equation for it to work, and it did. This is science discovering one thing, quite independently discovering something else, and fitting together in a way that no one was aware was going to happen. This is complementary science, and this is evidence that both are correct. Now, today we can measure the distance to the Sun because we can bounce energy waves off of it, and we know through Planck's constant, and I know I'm getting deep here for a second, but we can determine distance based on the sending out a signal and waiting for a return. Using the tools of their time, though, they did a phenomenal job and got high degree precision on distance. We've done further tests on Newton's laws of gravity, including tests in vacuum chambers, so they weren't able to conduct at the time to remove air resistance from the equation, and his formulas have been proven to be worked, and they are used in practical application all over the world, the rate of descent. And he said, if it works here, it works out there. That was a big notion. The idea that if it worked here, it also worked out there. And when you plug the same numbers that work here on Earth into that equation that another guy, quite independently, had come up with, and it all worked. The math still worked. The math helped us to understand something, and the cards, I'm going to say Cassini was a card, his work was a card, and Newton was a card, and they needed the others to be accurate, and they balanced out exactly correctly. The truth is, the world is round. The truth is that math can help us understand the relationship around us of the world, and that truth can set you free. The free from the lie and the trap that the world is flat. That is a lie. It's a trap. And I hope you guys will use the intellectual integrity and honesty in order to discover that for yourselves. This is Christian Truther, signing out.